You ever wonder why things just suddenly break? Why slow, steady pressure can all of a sudden lead to an explosive, totally unpredictable collapse? Well, today, we're going to dive into the work of a man who found a hidden geometry in the very act of catastrophe.
It's a question that honestly applies to everything. We see it all around us, in huge systems and in tiny ones. We try to build things to be stable. We expect change to be gradual. But let's be real. Reality doesn't always play by those rules. So what's really going on with these sudden shifts?
Okay, think about a stock market. Confidence builds up bit by bit. Prices creep higher and higher. Everything seems totally fine. Until, in a flash, it's not. The bubble just bursts, and all that value vanishes, poof, overnight.
Or picture a simple stream, right? For miles and miles, it's just flowing predictably, meandering along. Then, bam! A sudden drop in the landscape, and that calm, gentle water becomes a crashing, chaotic waterfall. It's a complete and total change of state.
And even on a microscopic level, a healthy cell can just be doing its thing, dividing normally for years. And then, some invisible line gets crossed, and it transforms into something else, something dangerous. See, these aren't slow burns. They are sudden breaks. They're catastrophes. And one man decided he was going to map them.
And that man was René Thom, a French mathematician who just saw the world in a completely different way. He wasn't just interested in crunching numbers. He wanted to understand the fundamental shapes of change itself.
So while a lot of his colleagues were deep in the weeds with calculations and abstract proofs, Thom was thinking bigger, way bigger. He saw mathematics as more than just a tool. He saw it as the language of the universe. He was convinced that numbers and shapes held the secrets to the very fabric of our world.
And listen, this wasn't some philosophical daydream. The guy had the genius to back it all up. Back in the 1950s, he was working in a field called topology, which is basically the study of shapes and spaces, and he came up with something called cobordism theory. It was this totally revolutionary way of classifying how shapes can connect to one another. It was so groundbreaking that in 1958 it won him the Fields Medal. That's like the Nobel Prize for math, okay? It's the biggest deal there is. But for Thom, that was just the warm-up.
So after winning the highest honor in his field, what does he do? He pivots. He turns his attention away from those pure, perfect shapes and starts looking at the messy, unpredictable stuff of the real world. And that's what led to his most famous and most controversial idea, catastrophe theory.
So what is it? Well, catastrophe theory is this really radical idea that you can use geometry, like actual visual shapes, to model and even predict these sudden, dramatic changes. The core idea is that even when a force is smooth and continuous, the result can be anything but. It can be abrupt, sudden, and discontinuous.
Let's make this super simple. The best way to get it is the classic rubber band example. Imagine you're stretching a rubber band. You're pulling slowly and steadily. The band stretches, it's stable, it's fine, right up until it's not. You hit a tipping point, and in an instant, pop, it's gone. That pop is the catastrophe. Thorpe wanted to figure out the mathematical shape of that exact moment of failure.
And what he found is, frankly, mind-blowing. He proved mathematically that for a huge variety of systems, every single possible sudden break, every fundamental catastrophe, boils down to one of just 7 basic geometric shapes. That's it. Only 7.
The implication of this is just massive. Let that sink in. This wasn't just a new set of equations. Thom believed he had found a fundamental alphabet for how nature changes, a universal grammar that could describe everything from a bridge collapsing to a dog getting angry.
This whole idea of a periodic table of change, how cool is that, was both beautiful and incredibly ambitious. And yeah, it definitely sent shockwaves through the scientific community. He laid the whole thing out in his massive 1972 book, Structural Stability and Morphogenesis. In it, he tried to build this grand bridge from the clean, abstract world of pure math to the messy, beautiful real-world patterns we see in biology, physics, you name it.
Now, the absolute rock star of these 7 shapes is the cusp catastrophe. It's this beautiful geometric model for any situation where a system is under stress and suddenly has to pit between 2 opposite extremes. Think about an animal that's been cornered. The stress builds, and it hits a point where it has to choose. Fight or flee. There's no middle ground. The cusp is the mathematical picture of that sudden, irreversible decision.
As you can probably guess, the reaction was all over the place. You had two camps. On one side, people were hailing it as a profound universal law, maybe the key to understanding complexity itself. But on the other side, critics were slamming its application to things outside of pure math, calling it controversial, even labeling it a pseudoscience.
But here's the thing. Whether you loved it or hated it, whether you saw it as a perfect law or just a flawed metaphor, you couldn't ignore it. The influence of catastrophe theory was undeniable. It absolutely changed how scientists thought about change.
In physics, for instance, it gave them a powerful new way to understand phase transitions. The easiest example is water turning to ice. The temperature drops smoothly, 1 degree at a time, and then, boom, it becomes a solid. That's an abrupt jump, and Tom's geometry turned out to be a perfect way to describe it.
Engineers got on board too for some really practical reasons. The theory is actually used to analyze structural stability, helping to predict the precise tipping point when a beam is going to buckle or a bridge is going to fail. We're talking about that razor's edge between a stable state and total collapse.
And in biology, it's used to model these incredibly complex events. Like, how does a single stem cell, which could become anything, suddenly commit and say, okay, I'm going to be a nerve cell? Or that sharp, non-gradual line between a state of health and a state of disease. The theory offers a way to map that.
So what's the big takeaway from all this? If you remember one thing, it's this. René Thom's catastrophe theory basically laid the groundwork and provided the essential language for what we now call modern chaos theory. He gave scientists a whole new toolbox to look at complex, seemingly unpredictable systems and actually find the patterns hiding inside. And this really gets to the heart of his contribution. René Thom's genius was seeing the structure inside the breakdown, the order inside the chaos. He showed the world that even the most violent, unpredictable events in our universe follow a kind of beautiful, hidden mathematical logic.
And that leaves us with this incredible, lingering question. If the moment of collapse has a specific mathematical shape, what other hidden geometries are out there, quietly shaping our lives, our societies, and our entire universe, just waiting to be discovered?